Okay, now that we've reviewed the slides, let's close the presentation, or just I'll remind you which one it is first. This is start to finish, video 3, I believe, and we'll start looking at the data trees for what files we have, and just peruse the inputs before starting the analysis. So in my main terminal window, as usual, I might start by cd to the home directory and type ls, which I was already in my home. We should see the AFNI Data 6 directory there. So let's go into that directory and start looking at what we have. cd AFNI Data 6 slash, if I hit tab, we can see everything that it has. And recall we want to go into the FT analysis directory. You had some classes under the AFNI directory. We'll go into our FT analysis. I'll hit tab again. And ls. Let's see what files are there. So the main files that we want to focus on here, files in directory, one, we have this FT directory, and two, we have a bunch of S scripts. These S scripts, the S0 something scripts, are generally all AFNI proc commands. That's why they have .ap.something. And remember, an AFNI proc command generates a proc script. So we also have corresponding proc scripts. So for example, S01 AP simple would generate S11. S02 would generate S12. So for example, if I just look at S01 tab, it's a very simple AFNI proc command. It doesn't do all of the registration stuff that we might normally do. That would generate S11. And if you look at S11, you can just, see the stuff that it does. Anyway, not too important. I'll use Q to quit out of less. But so those are the files, the proc commands and generated scripts that we have here. There's the tutorial directory I mentioned, ls tutorial. That's got a bunch of text files. Those are probably 7 years old. I don't know if the date will be accurate in here. 2010, okay, they're 10 years old. Whatever, close enough. But they still may be useful. They still contain a lot of descriptions of operations that might be worth reviewing if you're interested. Beyond that, what we'll focus on, we have some generated results here, but I'm not going to pay attention to that too much. Our original data is in the FT directory. This is the subject's ID, and so most things are named after that. So if we cd into the FT directory, we can see what's here and run AFNI and stuff, and make sure that this is the input for our analysis, the input data. So let's make sure we're happy with it. So we have a couple text files. Those are the stimulus timing files. I'll just cat them briefly. Cat EV star, so that's both of them. So that's the first one and the second one. We'll come back to that. But those are the stimulus timing files. Then we have the anatomy, brick and head pair. EPI run 1, 2, and 3, brick and head pairs. And a summa directory that we will promptly ignore here, but it's got all of our surfaces for this subject. So let's just verify that we're happy with the data here. So we can run AFNI in this directory. Again, just to verify where we are, our present working directory is AFNI Data 6, FT Analysis /FT. And if we run AFNI here, we can just make sure we're happy with the data sets in this directory. So there's the anatomical data set. Fantastic. I'll underlay an EPI. Looks good. If I open a graph window for the EPI, so I set the underlay to be EPI run 1 and then open a graph window, and I'll just hop around a little bit. You see we have a couple spikes in the data sets. We've looked at this in other classes, I guess, depending on what videos you've seen. So the spike at the beginning of the run here is due to pre-steady state, or our pretend pre-steady state time. And then there's a spike later on that we've looked at earlier and we are pretty sure that's just due to motion. If I ignore a couple time points with what capital I, now the scaling on the graph changes because those initial spikes are not being plotted. So only the downward spike really messes up the scaling. But now we can more clearly see some EPI function basically. Since our stimuli are long, the bold response to them is very long, and we can actually see it in the raw time series. That's not typical. It's not typical for a fast event design, which most are. So this looks great, and I'm going to look at one more thing. I'll set my underlay back to the anatomy, and you notice that the graph window just has numbers in it now, but it's still an axial graph window, but it just has numbers because there's no time series in this anatomical data set, so there's just one number. I'll close that. I can hit Q or use X or whatever. But I'll overlay the EPI data just for one run, for example, or even all three, just to see that it looks like it's in the right place. Looks great. It's not perfect, but that's okay. Well, registration is part of the pre-processing. But if it were like halfway off the screen or entirely off the image window, then we might be worried. We might need to help registration a little bit by getting them in the same ballpark before the registration programs take over. So this looks good. I'll note also that the EPI values, you can see 3000 here. If I go back and open a graph window for the EPI, you see the values are hovering around 1400 or so. If I right click on the graph window, the average value is 1372. So that's nice in that we wouldn't want to see average values around like 100 to 200, because these are typically stored as short integers being, say, 16-bit but signed, meaning only 15 bits of accuracy. So that means they can hold numbers up to 32,767, but they are still integers, and if the values only went up to like 100 or 200, then you can only tell the difference between 100 and 101. You can't tell anything smaller, and that difference between 100 and 101 is like a 1% change, and that's too big. So you've lost numerical accuracy. You've lost the resolution, numerical resolution in the data, so it's probably not going to work out for you very well for such an analysis. So you'd like these original numbers to be big, preferably over 1,000, but if they're 500, say, that's okay. That's a numerical resolution of closer to 0.2, which is still not great. But okay, this looks good. I'll close AFNI. So again, in this directory, we've got our two timing files. And let's just look at the first one now. If I cat av1viz.txt, it's just a text file. We could have typed this in. More likely, we've got some presentation software that was used to drive the stimuli for our subject, and it's recording the actual times of the presentation relative to the beginning of the run. And we just have some script that, or whatever program that automatically extracts our stimulus times from that. In this case, we have times that are multiples of 30 seconds. If you recall from the slides, our stimuli are 20 seconds long with a 10-second ISI. That means that the stimuli are starting 30 seconds apart. So the values in this file, you see there are three rows in the text file. They correspond to the 3 runs. So run 1, these are the stimulus times in seconds, not in like TR indices or time indices. They're in seconds. And they're real numbers. They don't have to be integers. They could be 58.36, whatever. But they're times in seconds from the beginning of the run. But importantly, when we give them to AFNI proc, we need to know whether the pre-steady state time has been removed from these. You can remove it or not, but you have to make sure AFNI proc handles it correctly. So in our case, we're planning to tell AFNI proc to remove the first 2 time points of every run. And we've already subtracted those 4 seconds from all of these event times. So at the scanner, maybe if you include the 4 seconds from pre-steady state, the actual stimulus events were at 64 seconds, 94 seconds, 124, etc. But then we subtracted 4 seconds from all of the stimulus events to account for the removal of the 2 pre-steady state volumes. So what's an example of how you could do that? You can use timing tool .py to remove. You can pipe this through last and remember Q to quit or space to page down. Example 2 here shows how you can input a timing file and add some offset. So we could have run this by adding an offset of -4 seconds and then write a new timing file. Note also that we've got hweb. If you run timing tool -hweb, it should open up the help on the web page. So this is the same help, but it's got the nice table of contents, and if you like it, it's written in the it's in an HTML document. That might be easier. So we can just click on example 2, and that's the same information. So that's how we make our timing files. And if you notice AV2 tab, enter. So if you notice the audio reliable timing in AV2.txt contains the other multiples of 30 seconds. So like the first visual event was 60 seconds into the first run. So at time 0 and at time 30 we had audio stimuli. And we have to know that we do know that these last 20 seconds each event, and we'll tell that to AFNI proc. One interesting little bit about timing tool. It's nice to evaluate the timing altogether. So if you've got 10 timing files, are there any strange gaps in them or something like that? You can actually do something like timing tool.py. Normally you'd say -timing, but we want to do things with multiple timing files. So there's actually a multi-timing option, and I'll just say avstar.txt, for example. That will get both of those timing files. And you can do something like -show events, and that will show the event list. You can even specify the stimulus timing duration. In this case, since we're using multi-timing, we have to use multi-stimdir, and we can just say 20 seconds. Or if there are 5 files, we could list 5 durations. But if you just use one number here, it just assumes that's the same duration for all the stimulus timing files. If you have duration modulation, which is to say within the timing file, if you have the duration attached to the event, then of course you don't need a stimdir. But we don't have that. We just have event onsets. So I'll do this. I'll tell timing tool that these are my timing files, and these are the stimulus durations, and please show the event list, chronological event list. And here's what it shows. So here's our command. It says there are 10 events across 2 conditions in run 1 and in run 2 and in run 3. So here's run 1. 2 classes, 2's and 1's for the second index and the first index. There's an auditory reliable at event time 0, duration 20 seconds, and then an auditory at 30, duration 20 seconds. And basically you can see the event times are all multiples of 30 seconds. the time diff, which is the difference from the end of the prior event to the current onset. So for the first event, that doesn't matter, but like the second event at time 30, the first event was at time 0 of duration 20 seconds. The second event is at time 30, so it's got a 10-second time diff from the end of the prior event. And you see these are all 10-second time diffs here. So that's good. And we can look at run 2 and run 3 and see the same thing. So it looks like we've constructed our timing files in a reasonable way. Each run has 10 events. They all end up at 270. All the time diffs are 10. That's great. Okay, just a little tool to look at timing files. So now that we think the input data all looks good, let's go back up one directory. Now we're into the FT analysis directory. So remember, these S files are the AFNI proc scripts, and in particular, the one we're going to run in this class is s05ap.uber, though actually we might modify it. But let's just briefly look at the text file now. Remember, you can look at it with less, s05, or maybe even AFNI open. If I did AFNI underscore open -e, please use an editor, then AFNI open will look for some editor in my system and open the text file using that editor. Maybe you like to look at it this way. I'll go back to using less. So here's the script we'll use, or approximately what we will use. And you can see we have a couple variables here. The subject happens to be one of our horses. Here's the command. AFNI proc starts up here, and you see again with all the backslashes, that means we're telling the shell that the current command continues on to the next line and the next line and the next line, etc. So we can't have any spaces after these. And there's the bottom of the file, so it ends up with execute. So we're also telling AFNI proc to not only generate a proc script, but to execute it as well. So AFNI proc will run the analysis here. It'll generate a script and run it. Now, does this command look like what we want? I'll make the window a little taller. Does this look like what we want? Are we happy with it? How does it compare to another script that was used in a lab that I used to work in? Or how does it work? How does it compare to a script from the same lab that was used to analyze a different set of data? We might want to answer these questions, and so I'll just take a moment and describe how to do some things with this file. So I'm going to type Q to quit out of this. And actually I plan to run, let me just cat the file again. This is going to generate a basic HTML review output. For those of you that don't have matplotlib installed on your systems, that would be appropriate. However, I would like to generate the matplotlib review output because it looks nicer. So I'm going to change this, and then when I start changing it, I can change it to do the extra, to ponder the options as we were discussing. So I'm actually going to copy S05 to the same file with the Pythonic at the end. If you can't run, if you don't have matplotlib on your laptop, and we'll check that in a moment, you don't have to run this one, but I'm going to generate a new file name just to play around a bit. So now let's edit this new one, and I guess I'll use AFNI open if I'm going to actually edit it. That way we can all do the same thing. Whoops, I forgot my -e. If you notice I'm hopping to the beginning and end of line, you can type Control-E to go to the beginning and Control-E to go to the end. That's often very helpful. So I'll edit the script. And here's the full AFNI proc script. And now the question is, how does this compare to a different one? There are multiple ways to compare it, but let me start by comparing it with some of the AFNI proc options. And in particular, one of our common ones that we suggest as a possible example for task analysis is example 6b. This AFNI proc command is actually more similar to example 6, but I'll add a new line here, and I'll come down. I'm not going to indent this perfectly just so the things that I do visually stick out, but I'm going to just add dash compare opts, and then I'll quotize, because there are spaces here, example 6b. So that means I'm telling AFNI proc that I wanted to look at this command but not to actually run it. By adding this, it's not going to generate a proc script. By adding compare ops, it's simply going to look at the options and compare them to those in help example 6b. So if I add this, now let's actually run the script. So I will save this. It's in a new file name. It's .pythonic, so I'm not overwriting the original, but I'll just save this, and now I'll run it on the command line. If I do ls-ltr to list files in long format with reverse time, so that the newer files are on the bottom, you see the Pythonic one is newer. It's got 2701 bytes, and there's an old one. Where's the Uber one? Here it is, 2668. So you see the file sizes are a little different. Anyway, let's run S05 now. So I'll do tcsh S05 tab, and I'll do .pythonic tab or .ptab. If I run that, it doesn't start an analysis. It just takes that current command, whatever is in the text file, and compares it to the target, which is example 6b. Oh, and it mentions for more detail, consider -verb 2. So we'll try that next. Then it generates some information, and I'll be quick about this just as a quick overview, but it says these are the options that are missing from the current command that are in the target. So I don't have an ADSCL, no. I don't have any anatomical followers, TLRC base, MNI 2009 SSW, and TLRC warp and TLRC warp dataset. So one thing we see clearly is that this example is not using nonlinear registration to the template, while the other one does. And that's reasonable, because well, maybe for making a video it's less relevant, but if you're like in a class setting and you want to run a quick example, you don't want to wait in a couple extra hours for nonlinear registration. So in this more simplified version that we're running here, we're just using affine registration to the template. So you do see those differences. And the other options in example B that we're not using is we're basically, in this case, we're going to use 3D deconvolve to use ordinary least squares regression to fit our model to the data. But in example 6b, we run 3D RemelFit to account for temporal autocorrelation in the noise model. So you see some differences. And anyway, you can do this sort of thing if you want to compare your command to a different command. Extra options specifies extra options in our current command relative to the target, and there are none in this case. Differing options are where we have the same option name but different parameters. And of course we have different subject ID and different anatomical and EPI data sets, some slightly different options for RegressOps 3D, and HTML review style, basic versus Pythonic. So the target one used Pythonic, we're using basic because we didn't make that change yet. So that's great. Just to show you very briefly, this says with verb equal to 1, it doesn't show all the details. But if we wanted to see all those, and if we didn't want this truncated to fit on the line, we can actually come back here and add dash verb 2 and save that. And that will provide those extra details here. So if I just up arrow and run the command again, now we see the same, basically the same output, but for example, the TLR warp data sets, we see the full names of all three of them, and we see the actual different subject IDs and data sets and stuff like that. So that's just a very simple example. If you're going to really compare your example against a different, that from a different script in your lab, for example, then you might use something more complex. Did I put that in this one? If I cat this file. Yeah. So this is more what you could do if you wanted to compare two full commands that are scripts in your group, say. So here's one full AFNI proc command. That's the current command, say, and I want to compare options versus options. And so these are all continuous. This is line continuation. This is all one long command, even though we start AFNI proc again. It's still options to the first AFNI proc command. So here's another full AFNI proc command, and we're basically saying compare all these options against all these options. And so that's what this example will do. If we actually ran that, it would look much like the other one. We don't really care about the details here. Oh, I'm sorry, I just catted the thing. If I ran it tcsh, then we see a similar thing. There aren't many differences here. Those are similar commands, but it's just meant to give you a demonstration of what you could do in your own group. So again, it's just two full AFNI proc commands attached together, but separated by compare ops versus ops. Any questions about that? Nope, good. Okay. So let's move on. So we wanted to run our basic AFNI proc script, but we wanted to change the HTML review style from basic to Pythonic. So I'm going to get rid of these this compare ops stuff. So now the command is basically back to where it started. But I'll change basic to Pythonic. And that'll be the only change against the prior file. And I'll save that. So again, this is going to be saved in the Pythonic file. And I'll just close this. So now if I, for example, just cat this file that we just created, it ends up with HTML review style Pythonic. And that's what we're going to run for the analysis. So maybe I'll just stop here. This is maybe a good breaking point, and we'll continue with the analysis in the next video.